Hi, everybody. So let's resume the second half of this lecture. And I do want to apologize for some of the previous lectures running over and there being a bit of a lopsidedness between one lecture being 50 minutes and the other 20 minutes. I am still working on how much time different things take to explain effectively. And I will say that when the divisions on the syllabus I have where I am like lecture 4A is this, lecture 4B is that, or lecture 5A or lecture 5B is this, those may be subject to small adjustments sometimes. I will not do any changes regarding what we're covering week to week and overall what we're covering from class day to class day. But thanks for being patient with little adjustments like that as we figure this out. I have taught this before online. It's just that this is sort of beta testing it online as opposed to alpha testing it online, I would say. So in this half of the lecture, we'll move on from talking about how water circulates at the surface and its relevance to Antarctica to talking about deep ocean circulation. And we'll close the climate unit with talking about climate research a little bit. Note that when I say climate unit, I mean that we'll be done with this week's discussion of why is the climate like this? We will talk about climate change much later in the course, and climate will come up over and over again throughout the course, especially when we talk about the history of Antarctica in terms of what its past worlds have looked like, what it looked like during the age of dinosaurs and even before that, because we definitely need to talk about how the climate plays into that. Now, the deep ocean circulation is known as thermohaline circulation because while surface water is moved by wind and the Coriolis effect, water is moved up and down the ocean water column by a combination of temperature and salinity gradients. The term thermohaline circulation comes from temperature, thermo, and salinity, haline. One way to remember that actually is that if you know the halogen elements like chlorine, salt is made of sodium chloride, chlorine is a halogen, that's where the word haline comes from. It's the same Latin root. Now, whenever we talk about air or water moving, a lot of it's going to be driven by gradients, by differences in pressure or differences in temperature or differences in salinity or overall distances in density. And water temperature can be changed a couple of different ways. Water can either absorb energy and change temperature from solar radiation, or it can lose it from contact with the atmosphere, with ice or other water masses through conduction, which was another method of heat transfer we talked about during the last lecture. How salty a particular part of the ocean is can be changed by inflow of rivers or melting of ice, which will release fresh water into the system and decrease the overall amount of salt dissolved in the water. Or you can evaporate water, taking away water as water vapor, or freeze some of the water, taking away water as icy water, and as ice, excuse me. And whatever liquid water is left becomes saltier. You don't have to memorize what happens at each of these different places, but the general pattern of what happens with thermohaline circulation is that water gains heat at the equator and loses it at the poles. And we're specifically going to talk about how in Antarctica, what has to happen is that the water has to get so salty and so cold in an area where it can sink for it to indeed actually sink and spread out underneath the water elsewhere in the ocean and move elsewhere throughout the world. Because remember, in general, things of different density don't mix well, and that will be a recurring theme through this half of the lecture. So water is going to get denser as you get colder until you form ice. Water is weird in that when water goes from liquid water to solid water, it does get less dense just from that phase transformation. And that is because water molecules have that sort of Mickey Mouse look to them, that sort of spread out look, and that causes them to face away from each other to avoid the positive end of the molecules from touching too closely. Water is polarized. Water Water molecules have essentially a negatively charged end and a positively charged end, and ice forms the way it does, aka very less dense and very more spread out, because of this. That is why ice floats. However, when water is liquid, as you get the water colder, it will get more dense. The water will get closer and closer together as the molecules move around less. Because remember, when something is hot, the molecules making it up are actually moving around more physically. And that's what causes water to vaporize too. If you pump enough energy in, the water molecules will move fast enough to be in a gaseous state. If you add more salt, that is going to make it denser because you're going to have the same volume of water, but there's physically going to be something else aside from the water molecules in there too. Salt has mass, so you have the mass of the salt and the mass of the water that was there in the same amount of area, roughly. And that makes salt water much denser. So the oceans, as I mentioned, are not equally cold or salty as you move up through the water column. And that's something that you can intuitively realize for yourself if you, say, go swimming and dive down and realize just how darn cold it gets the second you get away from the sun. In general, the water at the surface is going to be saltier because the sun is evaporating water more effectively. Also, this means that the water at the equator is going to be quite salty compared to, say, water at 30 degrees north or south, because sunlight so effectively shines down on the equator. It's so darn hot at the equator. The thing you want to think about is that the salt in seawater only really likes to be in the water when it is liquid. The dissolved sodium and chloride that make up the salt, that is not going to become a gas when the water becomes a gas. That doesn't easily happen. So if some of the water evaporates, like, say, the same way that if you boil water, those bubbles forming are water vapor leaving the water, but you still have some liquid water left. You could hypothetically boil the oceans away, but it's not going to happen with just sunlight. And we don't want the oceans to boil away, obviously. But the water that's still behind, the water that doesn't evaporate, now has more salt in it, essentially. It has the salt was left behind in it, and the salt is more concentrated now. The same thing. So what you end up with is something called the halocline for saltiness, like in this middle diagram. You get this zone where there is a front, essentially, a relatively rapid difference in the salinity between the surface water, which is heated by the sun, and the deep water, which isn't. And in addition to salt, that also just means that the surface temperature is going to be warmer, period. Like I said, you go down in the ocean, the sun rapidly becomes less effective at heating the water as you go deeper down in the ocean. And this makes temperature stratification. This means that there's a pretty rapid drop in temperature. And density overall is determined, seawater density is overall going to be determined by salinity and temperature. And you can mathematically put the thermocline, which is the temperature separation boundary, and the halocline, aka the salinity separation boundary, you can conceive of them together as the pycnocline, or the density separation boundary. And in general, the pycnocline is not something that a distinct mass of water crosses easily. Not a lot of water goes from the surface to the bottom of the ocean because they're so different in density. But the poles are a little bit different. The fact that the sun is so much weaker actually plays a huge role in this. The sun is weaker in that it's spread over much more land because of the latitude you're at. It's not being pointed directly at the equator. It's being spread out. The solar radiation just doesn't heat the surface of the ocean that effectively. So what that means is that the surface water is not actually all that much warmer than deep water. Something else that happens because you have sea ice forming and melting seasonally, as well as the fact that you don't get as much evaporation, period, from the sunlight being weaker, is that the surface water isn't going to actually be all that salty. The diagram on the right does a nice job of showing just how relatively little difference there is in salinity in the surface at the pole between surface and deep water at the pole versus at the equator. The consequence is that more mixing is possible. There is not as strong of a temperature or salinity difference, and so it's a little bit easier for a mass of water to either rise up from the surface and go to the top, or go from the top and sink down to the bottom. And that's a lot. And in fact, the big thing that happens in Antarctica is that water gets especially cold and salty at the surface, and then gets so dense that it just sinks down to the very bottom of the ocean. And it can sink because this density difference that normally blocks that from happening is not quite as strong at the poles. Let me return to sea ice and talk about another example of the salt not really going with the water when the water changes phase. When water freezes, if you have seawater, the salt is going to stay in the liquid portion of the water. And it's very, very hard to freeze. If you have a body of water, it's very hard to completely freeze it solid. Especially when we're talking about the ocean. There's usually going to be a little bit of liquid water left. And that remaining liquid water is extremely salty, which makes it dense. In Antarctica, it's already quite cold also. So you have really cold and really salty water forming to a big extent because of extensive sea ice formation, because there is so much ice forming on the surface of the water that it's essentially draining the ocean to some degree, and meaning that there's less liquid water and essentially the same amount of salt, making the whole situation much more dense. And the concept of a water mass involves you thinking of an often moving body of water within the ocean, in a sense that has a distinct temperature and density. And at the poles, what happens is that one of these distinct masses forms and can cross the picnic line, can cross the density boundary, because it's not quite as distinct. In Antarctica, the water sinks down to the bottom, and it will then undergo what's called deep spreading. Most of this water that forms in Antarctica and sinks down will travel northwards. It'll travel northwards along the seafloor to more temperate latitudes. By the point that it would start to all rise up, that it would have gotten just a little bit less salty and risen up, it can no longer cross the picnic line by that point. It travels northward to the point where you are in areas that do experience more intense evaporation at the surface, and where it's not quite as easy for a deep water mass to simply rise up the same way it does at the pole. So what happens actually is that the water from Antarctica kind of gets spread out all over the bottom of the ocean and gets spread throughout the ocean that way. And this is important for a number of reasons. One of them is that this water that forms at the surface and then sinks down is very oxygenated because it was at the surface, and it plays a very important role in bringing oxygen to the deep ocean, as well as spreading dissolved oxygen throughout the oceans. It also carries nutrients. It carries nutrients from where plankton could photosynthesize at the surface of the ocean, and carries those nutrients down deep in the ocean where there's no photosynthesis. The bottom of the ocean is dark, there's no photosynthesis there, but the movement of this bottom water to the bottom of the ocean carries some of those nutrients down and helps support life in deeper parts of the ocean, as well as just spreads nutrients around the world. Because something we'll talk about later in the course is that because you get this sort of burst of sunlight in the summer, the plankton go haywire, photosynthesizing and making food. And so there are a lot of nutrients in the Antarctic water. And when that gets taken down to the bottom of the ocean, that helps distribute those nutrients both throughout the bottom of the ocean and throughout the world's oceans in general. So an interesting occurrence that causes this to form is the existence of something called a coastal polynya. And a polynya is a gap. A coastal polynya is a gap that forms at the surface of Antarctica, a gap between the Antarctic continent and sea ice. And here is where the katabatic winds come into play once again. the pressure wind from the interior blows ice away from the shore. And what that does is that exposes seawater. That exposes liquid seawater that rises up. That causes new sea ice to form very rapidly. I wish this were animated, because what's happening is that the wind is perpetually pushing the sea ice away from the continent. New water is upwelling, new water is replacing it, and the surface of that water is constantly freezing and then being pushed out again, and then more water replaces it and is frozen. Why is the fact that the sea ice is forming important? It's important because if you get sea ice forming, if you get new sea ice forming, that's going to be essentially draining liquid water out of the water surrounding it. It's going to be putting the water into ice form and leaving a lot of salt behind, leaving a lot of very salty, briny water behind, really freakishly salty water. That water is already really cold because you're in Antarctica. It becomes extremely salty. So what does it do? It sinks. The cold, high salinity water sinks down, to a large extent because of the formation of these polynyas. And you can see in a satellite picture, that's why you'll often see a little bit of open water at the very edge of Antarctica, because the katabatic winds are constantly pushing away the sea ice from the coast and generating more sea ice formation, and thus generating the formation of this cold, salty Antarctic bottom water. And that's what it's called. It is a specific mass of water referred to as Antarctic bottom water, AABW, if you're going to go by acronyms. It is very salty and it is very cold. And what that does is that causes it to sink to the very bottom of the ocean. So it's the deepest identified water mass, in part because it sinks so deep because it's colder and saltier overall than any other water mass. And it will gradually spread towards the surface as it reaches more temperate latitudes, and it does mix. It's going to mix a little bit with other water masses, but for the most part, it stays a distinct water mass that's kind of actually sinking underneath other less cold and less dense water masses from elsewhere. You'll notice this diagram has NADW, and that is North Atlantic deep water, which is similarly cold and salty water, but not quite as cold and salty water that forms in the North Atlantic Ocean, in the Arctic. So there is a similar process actually happening up north in the Arctic. But there's also simply so much Antarctic bottom water that helps it be detectable as a distinct entity as far north as 50 degrees north. And they can sometimes find it as north as the equator even. The Antarctic bottom water is formed in a couple of specific locations. It's actually mostly formed in the seas, the little inlets in Antarctica, like the Weddell Sea and the Ross Sea, in part because there's more chances for coastal polynyas to form. And I'll talk a little bit about how researchers have identified that there has to be kind of a specific set of conditions for there to be consistent enough formation of coastal polynyas for Antarctic bottom water to form. And here's another view of it. The Antarctic bottom water that we're interested in is this sort of turquoise layer that you can see just sinking along the continental slope, sinking along the edge of Antarctica and ending up at the bottom of the ocean. And you'll notice that the bottom water is kind of, to a big extent, moving in a different direction from the water at the surface. The water at the surface is being dragged along by the wind, but there's also just water sinking deep into the ocean and spreading out over the bottom of the ocean as it heads north. You really have to consider deep ocean circulation and surface ocean circulation as two different beasts. And you'll notice that I mentioned that the North Atlantic deep water, the equivalent of Antarctic bottom water in the Arctic, is actually flowing over the Antarctic bottom water here because it is not quite as dense, not quite as salty, and not quite as cold. And I want to point out that while Antarctic bottom water might be the singularly most voluminous and the most interesting water mass related to Antarctica, it's not the only one. Ocean circulation is complicated, and you're going to have a lot of different individual masses of water to consider. One, for example, is the Antarctic surface water that transforms into what's called Antarctic intermediate water, which is another another distinct water mass from Antarctica that can be found much farther away from Antarctica itself. Antarctic intermediate water forms as surface water that is flowing away from Antarctica sinks at the polar front, aka the Antarctic Convergence. So the Antarctic Convergence is actually a zone where water is being forced under. You have masses of water being pushed towards each other that don't mix very well. And the Antarctic surface water gets pushed under and becomes a new mass called Antarctic intermediate water. Antarctic intermediate water is going to be less dense than either Antarctic bottom water or North Atlantic deep water, so it's going to spread out at at kind of a middle depth in the South Atlantic Ocean and the South Pacific Ocean, and it will also do its part in bringing nutrients and oxygen out towards the oceans. But it is something interesting I want to point out with this diagram is that you can actually trace Antarctic intermediate water getting as far north as the North Atlantic. And at the North Atlantic, you actually have something funny happening with the water coming out of the Mediterranean, because the Mediterranean Sea is excruciatingly salty because it's so landlocked, because there's a very narrow channel of water to get out of it, the Straits of Gibraltar, the tiny little gap between Morocco and Spain. As soon as that water gets out to the rest of the ocean, it sinks right down because it's so darn salty. And you can see that it actually sinks below Antarctic intermediate water, but not below the North Atlantic deep water as a result of that. Now, I mentioned convergence and how a front involves masses of water being forced together. Something that happens with ocean circulation is that you can either have divergence or convergence if you have distinct masses of water moving. If distinct masses of water are moving in opposite directions, or if you have a mass of water being pressed up against the coast, that will cause divergence. Water will be pushed out in different directions, or water will be pushed away from the coast, and water will rise up to take its place. This is actually really important for the exchange of gases and nutrients, and this is happening in California. In California, the wind pushes the water away from the coast, and deep water rises up, bringing in nutrients and oxygen from the deep ocean. So that's one place where wind actually does factor into ocean circulation, because the wind can play a part in pushing air from the coast, or in the case of the katabatic winds in Antarctica, pushing ice away from the coast and generating coastal polynyas. You can actually also have polynyas out in the open ocean. You can get another type of polynya called an open ocean polynya when two different water masses are pushing away from each other, away from the coast. So you get coastal polynyas if you have divergence at the coast. You get open ocean polynyas if you have masses of water separating away from the coast. If you have masses of water approaching each other, one is going to be forced downward, and that's going to be at the front. There's going to be a little bit of mixing in that very narrow zone where the water is being forced under, but for the most part, the denser water is just going to go under the less dense water. And that is what happens with the masses of water leaving Antarctica. That's what happens to Antarctic intermediate water as it comes to hit warmer water away from Antarctica. So that's most of what I want to introduce in terms of general concepts related to circulation. I next want to go over the articles I had you read and the video I had you watch to kind of talk about how some of these concepts apply to research that's being done. So I had you read the article about Antarctic bottom water to give you a sense of the fact that a specific set of conditions have to occur for a specific region, like say the Weddell Sea, to be a nursery for Antarctic bottom water. Antarctic bottom water doesn't form consistently all around the continent. You need to have a coastline that's going to be the right shape. You need to have relatively deep water nearby acting as a pool. The water has to be able to sink deep enough. You have to have especially strong katabatic winds, and those katabatic winds have to blow year-round. Basically, they have to be able to constantly be forming a coastal polynya. And the point of the article was that Antarctic bottom water is forming at a pretty consistent rate right now, but that rate could change if climate conditions were to change in Antarctica. For example, if you have the permanent ice shelves coming, the ice shelf coming from the glacier and extending over the ocean, if the shape of those ice shelves changes, if you simply have less of an ice shelf extending over the extending over the Antarctic Ocean because global warming has caused them to break up, well, that might actually change whether you have polynyas forming or not. If you have less sea ice forming, if you have sea ice forming being inhibited by lower temperatures, the water underneath will not be as salty, and Antarctic bottom water will not form. And if the rate of Antarctic bottom water formation changes, that could actually have pretty strong consequences for thermohaline circulation elsewhere in the world, because you'll simply have less of this cold, nutrient-rich water being delivered to the Pacific Ocean and the Indian Ocean. And that's going to affect conditions in those oceans. And I say conditions because it's hard to predict exactly what's going to happen if the rate of Antarctic bottom water formation changes, but it's a less frequently talked about potential consequence of climate change. Because if the shape of the coastline changes in Antarctica, and if the climate in Antarctica changes, if sea ice isn't forming as effectively, or if the katabatic winds start to weaken, well, that means that the circulation patterns are going to change. One of the other articles I had you read talks about the Antarctic Circumpolar Current and how people study it specifically. The thing I found interesting about this article is that they came up with data that showed that the current was moving faster than had been predicted for a long time. And they considered the possibility that the winds had gotten stronger, and that was what was driving the current and moving it faster. But they looked at meteorologist wind speed data, and they didn't find anything that indicated that the winds were absolutely what had gotten stronger. And they came to the conclusion that they simply had better data, that what they did to collect the data was they placed gauges inside of glass spheres on the ocean floor, about 30 kilometers apart, and those spheres simply sat there, and the scientists crossed their fingers that those gauges inside of those glass bells would not be broken, and they just collected data as to how fast the water was moving over the course of however long the study was. And the reason they chose to do it here, south of Argentina and Chile, is because south of that is the Drake Passage, the narrowest distance between Antarctica and any other continent. It's extremely stormy for that reason. It's where the current moves fastest, and as we'll talk about later, getting through this on wooden ships was a nightmare. That's why getting from the Atlantic to the Pacific Ocean was a challenge, and getting anywhere near Antarctica was a challenge because this area is so windy. And remember that the Antarctic Circumpolar Current movement is measured in a quantity called a spheredrup. A spheredrup is a rate. It tells you how many cubic meters of water are being dragged per second. And they came up with a much bigger estimate than before, 173 versus 134, which is noticeable. So I think it's interesting that they simply published that better resolution data, like having more gauges gave a better and more accurate picture as to how fast the current was moving. The last article I had you read was about Lake Vostok, the coldest place on the coldest continent on Earth, in the sense that the coldest temperature ever recorded on Earth was at Lake Vostok, 128.6 degrees Celsius, which is more than 50 degrees colder than average. And this article outlined a study into why that particular polar winter was so cold, because it had not been well understood for a while. And what they looked at was the flow of air, and they discovered that there had been an especially intense flow of cold air from the interior of the continent at that time. So intense that the relatively small amount of the relatively warm air from the ocean that normally rises up at least a little bit onto the plateau and flows to the interior, there is a little bit of that. That was just completely stopped, almost, because the cold flow from the interior was so intense. There was also no cloud cover at the time, and this simply allowed more of the heat to escape out into space. So it was a combination of circumstances producing really extreme weather. And it's a good indicator that even though in both natural and artificial settings, we don't necessarily know what the consequences of a change such as a current of wind flowing differently. We don't know what the consequences of that change would be. Um, People wouldn't necessarily have guessed that that relatively insignificant wind pattern change would result in such a cold winter here at Lake Vostok, but they have the numbers to show that it did. The film clip I had you watch was the Antarctica portion of an episode of Frozen Planet, which unfortunately focuses, the series as a whole tends to focus on the Arctic more, which I think is fine, which is fine because the U.S. does more Arctic research. The U.S. is the well, actually it's a BBC production, not so what the U.S. does is not really relevant. But the Arctic is more accessible for scientists, both from the U.S. and from the U.K. and from elsewhere. And also the series talks about the indigenous people of the Arctic, which I think is great. So the bits on the Antarctic are shorter, and when I have you watch clips of this, I just kind of show you where to watch the Antarctic stuff. But the takeaways from this clip are that the human history of Antarctica is a lot shorter and a lot more singularly focused. There has never been simply a group of people living there just to survive. People have gone to Antarctica either for glory, to be the first to explore it, the first to get to the South Pole, or to do research. I like the clip because it illustrates just how dark the polar winter is, and it gives a nice example of how humans have kind of had to adapt, the same way as we'll talk about that many of Antarctica's modern wildlife has had to adapt, such as using blubber to deal with the cold, or huddling penguins, using that to deal with the cold, or insects literally freezing. Humans can't do any of those things, so what humans have done is they've built better shelters. They store food, because I mentioned that because in the winter in Antarctica, you can't leave. No flights can really go to Antarctica. No one can really leave Antarctica either. So you have to make sure you have enough food there, and humans have adapted by learning to store food. Humans have also adapted by kind of generating their own light to allow some growth and some food production to happen during a period when no growth happens. Because Antarctica ecologically is weird in that for a good portion of the year, there is no growth and no photosynthesis at all. And one way in which humans have adapted to that is they've brought greenhouses. They've artificially created growth and allowed there to be some food production on the continent. Not much, they're small greenhouses, but it's an interesting adaptation on the part of humans either way. But how did we get here? How did we get to Antarctica being this cold wasteland, essentially? Well, Antarctica has not always been isolated. It was once attached to South America, as well as to the other southern continents, but most recently also to Australia and New Zealand. And think about what this would have meant for Antarctica during the dinosaur age. There would have been no Antarctic circumpolar current. The current would not have gone all the way around Australia, if that's what you're wondering. Australia is way too far north for that. And there were no ice caps either, which means no katabatic winds and much lower albedo. You're still going to be really close to the South Pole, so you're still going to have the polar winter, and the sunlight in general is going to be weak. So even in the dinosaur age, the Antarctic had a distinct climate and ecosystem, if one that wasn't quite as extreme as it is now, but it was very distinct from other parts of the world during the dinosaur age, and we'll talk a little bit more about that in the coming weeks. How we study this depends a lot on proxies. How we get any understanding of what climate has looked like in the past comes from the science of paleoclimatology. We can't go into the past with a thermometer or a wind gauge, but we can make educated guesses about we can use remnants from the past, like ice cores or fossils or sediments, to make educated guesses about, say, how cold or windy was the area where this thing was when it was alive. And those proxies can be a number of different things. They can be something we'll talk about when we talk about glaciers, is that distinct layers of sediment are deposited when glaciers melt during when it gets warmer, and you have glacial meltwater carrying clay with it. Those are called varves. You can also look at the sediment in the ocean, and that's actually what a professor at UCSB has done. Alex Sims used to take trips on the research vessels to collect ocean sediments, largely to look at patterns over time, and to look for little fossils inside of them. Because the fossils are of ocean plankton, and how abundant the ocean plankton were, or also what specific types were alive, can tell you about the climate. Not as commonly in Antarctica, but elsewhere, you can look at the chemistry of the calcite minerals making up cave formations to track climate. You can also look at tree rings, which is not very helpful in Antarctica because there have not been any trees in Antarctica for millions of years. However, millions of years ago, there were trees in Antarctica, and we know this because we have fossils. We have fossils of dead plants that show us that Antarctica at one point had a climate that was warm enough to support forests, which we'll talk more about in the coming weeks. Lastly, you can use ice cores. You can use the chemistry of air bubbles trapped inside of the ice to measure the chemistry of the atmosphere, particularly the concentrations of CO2 and other greenhouse gases. Because in general, if the atmosphere had more CO2 and other greenhouse gases, it's going to be a warmer climate. And we can see how that's changed over time by looking at the air bubbles that are trapped inside of glacial ice. Whew. So that is it for now on climate, at least in terms of that being our main subject. I will not be recording a lecture on Monday. Most of you know the history of Martin Luther King, but I will just briefly say in his honor, he is the only African American honored with a federal holiday in the United States. He was a civil rights leader in the 1960s who pushed for an end to enforced segregation in the South, but also in general in the United States. Unfair voting laws, laws that targeted where Black people and other minorities could live. This picture is from his famous his famous "I Have a Dream" speech given after the March on Washington, and he was assassinated. He was assassinated while he was still actively working as a civil rights leader, and at a point where he definitely would not have considered his work done. And the holiday was set aside to honor his legacy and the legacy of those also who continue to work for equal civil rights, not just for African Americans, but for other groups of Americans that have suffered discrimination. So in his honor, there will not be a lecture on Monday or a discussion section. We will be resuming lectures next Wednesday, when I will post my first lecture about geology. So enjoy your weekend. Hope if you can take it as a long vacation weekend, I hope you get the chance to enjoy that. And I will be around for office hours or by email for questions if you have any.